Let me know when I can start.
Yes, we can start now. So today's second speaker is Sagarika Tripathy from Indian Institute of Astrophysics, Bangalore, and she's going to talk about unraveling the origins of magnetic fields in the early universe.
Um, Hi, good afternoon, everyone. I'm Sagarika Tripathy from the Indian Institute of Astrophysics, Bangalore. So first of all, I would like to thank Anis for giving me this opportunity. So as the title suggests here, I'll be talking about the generation of magnetic fields in the very early universe around the epoch of inflation. So just to give a brief idea, this I will be talking about these three papers, not entirely, but selected results from these three papers, which I have done in collaboration with Dr. H.V. Raghavendra, Dr. Devika Chaudhary, Dr. Rajiv Jain, and Professor L. Sriram Kumar. So the outline is as follows. First, as I am going to talk about the generation of magnetic fields. So first, I will start by introducing what is the observed strength of magnetic fields present in the current universe and what could be their possible primordial origin. Then I will discuss the challenges in generating these magnetic fields in single field models of inflation involving non-trivial dynamics such as deviation from slow roll, that is which Mian has just talked about. An epoch of ultra slow roll is there in the model itself, which is generated by the inflationary model. So I will be discussing some of those models where an epoch of ultra slow roll is allowed and how they and what happens to the primordial magnetic fields during those epochs, how do they behave, and if we try to generate those magnetic fields in those kind of inflationary models. I'll particularly discuss what are the challenges in generating these primordial magnetic fields in those models. Next, I will talk about how we circumvent those challenges firstly with the help of two-field models of inflation. And then another alternative is by constructing a coupling function that contains the derivative of the scalar field in Platon. So I will elaborate what are these methods that we have used. Then before concluding, I will talk about what are the imprints of these primordial magnetic fields which we have generated during inflation on the cosmic micro background spectra. So, just to give a brief picture of these observed strengths, so we know that in Earth, the strength of magnetic field of Earth or the surface of Sun is of order of 1 Gauss, while the strength of magnetic field in galaxies and cluster of galaxies is of order micro Gauss, which is coherent on length scales ranging from kiloparsec to megaparsec. Well, so these magnetic fields in galaxies and clusters are expected to be generated by the amplification of some pre-existing weaker magnetic fields by physical phenomena like dynamo mechanism. So these seed fields, which the weak fields that initiate the dynamo, so we are interested in those seed fields, and to understand the nature of those seed fields, it is difficult to just look into the data obtained from galaxies and clusters, as there are a lot of uncertainties involved in this dynamo mechanism or the battery mechanism, whatever they use to generate these magnetic fields. So, in order to understand the origin and nature of these seed magnetic fields, we need to look into regions in space where these magnetic fields, if once generated, are expected to stay in their undistorted form. So, one such region is your intergalactic medium voids, where if the magnetic field was present at very early times due to absence of any magnetohydrodynamical processes or plasmas, so they are expected to stay in their undistorted form throughout the history of evolution. So now, to understand the origin of these magnetic fields, first we will understand what are the bounds on these magnetic fields, because there is no direct observation to those magnetic fields present in the voids. So I will first briefly explain what are the bounds on these magnetic fields, and then we will go back how these magnetic fields could have been generated. So this is a summary plot of the theoretical and observational constraints on the magnetic fields present in the voids. In my work, I was particularly interested on these large-scale magnetic fields, which is presented in the steel region, which ranges from with a lower bound of 10 power minus 17 Gauss, which this bound is obtained from the observations from these high-energy TeV gamma ray blazars. And the upper bound comes is of order of 10 power minus 9 Gauss, which is one non or approximately 1 nano Gauss, which comes from Faraday rotation measurement of different quasars and CMB observations. So, to understand these large scale magnetic fields in this strength range, so what we propose that okay, these magnetic fields could have been generated during the inflationary epoch of the early universe. So, to understand these magnetic fields, origin of these magnetic fields during an inflation, so I will briefly explain what is inflation first. So, thanks to Mian, he has already explained elaboratively what is inflation. So, I will just briefly explain how I see it. So, as you can see here, if this inflation region is not present, these modes of observational interest, which are observed today as homogeneous places, there is a homogeneous temperature of 2.7 Kelvin of CMB, which suggests that all these modes of observational interest, the length scales of observational interest, are ought to be present within the horizon of each other to share the same thermal property. So if this region of inflation is not present on the left side, we see that it's very less likely that at any point of time at the very beginning, these modes have interacted with each other. However, if we introduce a period of a decreasing Hubble radius, we see that all of these modes, you can consider the different kinds of modes with different length scales, and it's if there is a decreasing Hubble radius, we can say that okay, these modes would have interacted at way before recombination, and this period is known as the inflationary epoch. So what is the condition for inflation we need is we need to have an accelerated expansion. This is a condition required to have a decreasing Hubble radius, which is AH inverse, as you can see here. And this A double dot, this acceleration greater than zero, if you substitute it in the Friedman equations, you will obtain this energy condition, rho plus 3p less than zero. Now, to satisfy, what is the simplest way to obtain this, satisfy this condition is by introducing a scalar field slowly rolling down a potential, and this can justify inflation as it satisfies the equation. So the equation of motion, as you can see for the inflaton field, is governed by this equation. And here this is the drag term, which ensures that we have enough inflation for all the observable modes to be within the Hubble radius. So H is the Hubble parameter, A is the scale factor, and to ensure we have sufficient number of E folds for inflation, we introduce certain slow roll parameters, which is defined as this ratio, and the higher slow roll parameters are taken as to be derivative of the first slow roll parameter. Just sorry, the preceding slow roll parameter. So as just I have mentioned a quantity called E folds. So the E folds are nothing but it's a unit, dimensionless unit of time, which is basically the logarithm of the scale factor. So now let's understand. So I hope this idea of inflation is clear to everyone who is listening to the talk. So next we will understand how magnetic field can or cannot be generated during inflation. So there is a small problem with generating magnetic fields in the typical setup of inflation. If you use this standard electromagnetic action, and we do a conformal transformation, we see that the standard electromagnetic action is invariant under conformal transformation. So under this setup, the energy density of the magnetic field rapidly decay as inverse of the fourth power of the scale factor. So that is, if the inflation is proposed to be exponentially expanding universe, and as I showed earlier that the if I change everything in terms of E folds, so I see that the energy density, even if I generate some small amount of magnetic fields during inflation, it will rapidly decay away during inflation itself. So I need to preserve the energy of electromagnetic fields generated during inflation, so that it can evolve to present day strength, which is the range of amplitude I have shown in the first plot. So we need to break this conformal invariance of the standard electromagnetic action. So there are certain ways discussed in several literatures. One is by coupling the electromagnetic action to the Ricci scalar, Ricci tensor, Riemann tensor. So this is one such way. Another is by coupling to the action. Then the third one is coupling the photon to the scalar field in photon, which is what we follow. So all my description of generation of magnetic fields will be where the photon is coupled to the inflaton field. So this is how the modified action look like. As you can see here, this is I have introduced a coupling which couples the electromagnetic field with the inflaton field. And another term present here, which is a dual of this, which is generally introduced to generate helical magnetic fields. So in helical magnetic fields, typically what happens, they are more of observational interest, the helical magnetic fields, because the helicity can affect the polarization of CMB observations, and they can also affect the chirality of gravitational waves. But I'm not going to those stuff. I'm just introducing that there can be an extra term which can be introduced to violate the parity. So then varying this action, we can arrive at the equation of motion, and we redefine this vector potential in such a way that we can see a similar form to that of a Mukhanov-Sasaki equation, which we encounter in case of the scalar perturbation or tensor perturbation. So we redefine the standard vector potential where we multiply the coupling function with the vector potential and redefine a quantity script A, and the equation of motion is of this form. So as we see, so here we impose the same initial Bunch-Davies vacuum condition when k is much larger than these terms, or k and then when it's outside the Hubble radius, or we say the modes have exited the Hubble radius, we then compare this k with these two quantities. Now, so then from the energy density, we define the power spectrum in terms of the energy density of the electromagnetic fields. And this is how it looks like. So now we are familiar with all these F mu nu and square root of minus G and everything. But the only parameter which we are not sure about is the coupling function. So our goal is to construct these coupling functions for different models of inflation, which are already have been verified with data. There are standard scalar power spectrum to it. So we are just constructing the coupling function for those models of inflation, and we are trying to see if magnetic fields can be generated in those models. So first one is the standard de Sitter inflation, we propose it. It has already been proposed in many literatures that the coupling function behaves just as a power law of the scale factor. And we see that in those cases, the power spectrum of magnetic field behaves scale invariantly for n equal to 2. So now we are using this particular form and this particular value as a reference, because the standard de Sitter is always used as a reference for there is a these slow roll models, which is often called as quasi de Sitter or near de Sitter models. So this, I would like to emphasize once again that this particular form of the coupling function, which leads to a scale invariant power spectrum of magnetic field for this particular value of n, is going to be our reference to compare against other models. So here is one example. For if my gamma is 0, that is if I turn off the parity violation, I see that the strength of magnetic field is scale invariant because H is a constant during inflation for a d Sitter inflation, and the electric spectra behaves as k square eta square. So now, just to this is the you can one thing come to our mind that if this is at the end of inflation, how do you obtain the present day strength? So to compare the strength of magnetic fields from the end of inflation to present day strength, we evolve the magnetic field. And so to understand the evolution, first we just define a parameter which is a smoothened amplitude which can be expressed as an integration of the strength power spectra of magnetic field. And then we evolve this quantity through this relation. And if we say that at the end of inflation or during inflation, the Hubble parameter is of the order of say 10 power minus 5, which can be roughly taken considering that the scale invariant power spectrum at the pivot scale is 2.1 into 10 power minus 9. So for that, we can see that present day strength should be around 10 power minus 12 Gauss. But depending on this H, we can obtain the range from 10 power minus 9 Gauss to 10 power minus 17 Gauss. Our upper bound should be the magnetic field strength should should not exceed the upper bound of 10 power minus 9 Gauss. So this is a very rough example for a typical de-Sitter setup where we are just considering a power law form of the scale factor, where this you can roughly see that end of inflation it is around 10 power minus 20 MPL power 4, and with doing some conversion you can arrive at this quantity. So this is all for de-Sitter. So if we move on to a more realistic scenario where inflation is driven by a scalar field, it is only justified to construct a coupling function, which is not just a function of time, but actually a function of the field. Because when you are coupling, you need to couple a field with another field. So this is our major work, that we construct a coupling function which is model dependent. That is, depending on the inflationary model, we try to use the behavior of the field to construct the coupling function and how it reflects the behavior of field in the power spectrum of the electromagnetic fields. So as we saw earlier that in a de-Sitter case, this is the kind of behavior of the coupling function in terms of E fold, which leads to scale invariant spectra of magnetic field when this n is 2. So what we do in our work is we solve this Klein-Gordon equation driving the inflaton field in the slow roll limits. Then using that solution of the field phi, we construct a coupling function which will ultimately behave in this manner so that for some choice of this n, we can arrive at a scale invariant spectrum to compare it against the de-Sitter results. So this is a plot of how a typical slow roll model behaves. So this is how the potential looks like. The first slow roll parameter, it has a very small value in the beginning and it gradually increases to 1 at the end of inflation. So using the slow roll solution of the field phi, we construct a coupling function. And when we plot a log linear plot, we see that here that the coupling function is directly exponentially growing as a function of the E fold. And for this kind of behavior, I will show what happens to the power spectra of magnetic fields. So this is a list of slow roll models of inflation, which we have worked on. These are the corresponding potentials, and using these potentials in the Klein-Gordon equation governing the field, we have constructed from the slow roll solution we have obtained. We have constructed these coupling functions. They look very complicated, but ultimately they lead to a behavior which we have constructed by the choice of these n's that will lead to scale invariant behavior. So as you can see, in comparison to the slow roll the de-Sitter, where there was a scale invariant behavior, we also could obtain a nearly scale invariant behavior in these slow roll models of inflation. And okay, so the dashed lines represents the helical field and the solid lines are non-helical field. And as you can see, these range of values are around 10 power minus 20 MPL power 4, which I have shown in the de-Sitter case, that range that can lead to a value of around 1 nanogauss present-day strength. So these models are, if you tweak the gamma, which is the helicity parameter, you can reduce these values. And we can see that these slow roll models can lead to generation of magnetic fields, which can evolve to present day observed strength. Well, although the slow roll models of inflation are in well agreement with the CMB data, however, with the rising interest to understand the generation of primordial black holes or to fit the improve the fit to the CMB data over lower multipoles, there has been proposed varieties of models which generates features in the scalar power spectrum. So we just saw some of the USR models by Bian just in the previous talk. So these are the 5 models which I will be talking about. In 3 of those models, as you can see, the features are generated over the CMB scale. This is one particular model where the power spectra is extremely suppressed. These are scalar power spectra, if not to get you confused. These are scalar power spectra which are obtained by the two-point function of the curvature perturbations. So my goal is to study the generation of primordial magnetic fields in these models. So as you can see, the first one is just, there is a small feature here with just small oscillations in the intermediate scale. And there is a very small separation of power over in this model also. However, in this model, there is a very large separation of power. Similarly, these two models generate features over small scales. Sorry, over these models generate features over small scales, and there is a very high amplification of power on these scales. And these models are very interesting from the perspective of generating PBHs after inflation. So now let's understand how magnetic fields can be generated. So this red one is the model with the step, the potential with the slow roll potential I had enlisted before. So this red one represents a model with a step, one of those models with a step. This blue one is the Starobinsky potential. I will show the form of the potential. Then these green one and these two are potentials which involve a point of inflection in the potential itself. So the first, as I said, is the whatever slow roll potentials I have shown here. If we just introduced a step to these potentials, so this is the form of the step in the potential. And as we can see, if we compare this with whatever scale invariant spectrum we have obtained earlier, that we see that there are not much difference in the behavior of the power spectra of magnetic and electric fields. However, because we have constructed the coupling function using the field phi, so when there is a step in the potential, the phi behaves a little differently, and that is getting reflected in the behavior of the coupling function, which leads to these small features in the intermediate scales in the spectra of magnetic and electric fields. However, since these are well within the range and these steps are very small, so these features are not very much of concern. The next category of model is the Starobinsky model, where there is a sudden change in slope between two slow roll regions. And due to this sudden change in slope, it gives rise to a brief deviation from slow roll. And this brief deviation from slow roll can be reflected in the evolution of the field. And we have constructed the coupling function here again, using the slow roll behavior of the field in these two regions and patching them up. And we managed to get the spectra of magnetic and electric field of the required strength. However, as you can see, there are features in the intermediate scale where this is due to the behavior of the field in this particular region. So there are oscillations which are unavoidable. However, again, this strength is also in the desired range. But then comes the point, the models of concern. Those are the models which involves a point of inflection in the potential. So as I have mentioned earlier, there are three models which involve this point of inflection. So this model, the first punctuation inflation model, generates features over large scales, while these two generate features over small scales in the scalar power spectrum. So now we will see how these models, what is the behavior of power spectra of magnetic and electric field in these models uh, yeah, in these models. So as you can see in such potential, just to briefly introduce how these epoch of ultra slow roll happens when there is a point of inflection involved. So the field slowly rolls down the potential. As soon as it reaches the point of inflection, its velocity sharply drops and the field hardly evolves, because as you can see, there is a flat region in the potential. So when the field becomes stagnant, it gives rise to an epoch of ultra slow roll. So in such scenario, what happens is, as you can see, the velocity is dropping sharply, and epsilon 1 is nothing but your velocity square by 2 mpl square. So as you can see, the velocity is dropping sharply. And when we construct the coupling function using a constant field, because the field has almost stopped rolling in this region, we see that the coupling function becomes constant once the point of inflection is reached. So what is the meaning of the coupling function becoming constant? That means that the magnetic field, the action, it has restored its conformal invariance and it cannot generate magnetic fields anymore. So however, this is very early in the times of inflation, or in these cases. So what we need to do is we need to ensure that the coupling function always grows exponentially to ensure we obtain the required behavior and strength of the magnetic field. However, in these models, because the field becomes constant, when we construct the coupling function using the solution of the field, we get a constant coupling function. So using that coupling function, if we try to obtain the power spectra of magnetic and electric field, we see that Until the field has a slow roll behavior, for those modes which are exiting the Hubble radius in that region of slow roll inflation, they can still show a scale invariant behavior. But for all other modes, since the conformal invariance is restored, they behave as k power 4, which is a typical behavior of a plane wave in a Minkowski background. So these modes, once the coupling function is constant, since they are in the Minkowski background, they cannot feel the expansion or they cannot generate electromagnetic fields. Another issue with here is, as you can see, even though some modes show scale invariant behavior in the slow roll regions, their amplitude, as you can see here, is extremely suppressed. While in the slow roll case, I was expecting a behavior of 10 power minus 20 MPL power 4 or some values around in that range. Here, as you can see, it's extremely suppressed in for these modes. These are the two reasons, which is why these models are not suitable to generate magnetic fields, or I can say that the way we have constructed the coupling function, these are the two ways to interpret it. Either the models are not suitable, or the way we are constructing the coupling function in the standard way, aiming to the exponential of e fold, we are aiming to the behavior of exponential e fold. That is not the suitable way of constructing the coupling function. So first we will address how, if these models are not suitable, but we need to see how the behavior of magnetic field for models which generate features in the scalar power spectrum. So we have shifted to two field models of inflation, which show similar behavior in the scalar power spectrum to that of the single field models of inflation. So, just to give a brief introduction to how the two-field dynamics works. So, the two-field models are, the action is governed by two fields. One is the canonical scalar field phi, and another is the non-canonical scalar field chi, with f of phi being the coupling function, and the behavior is of this manner of f of phi. So, when this b phi, for non-zero value of this b phi, there is a turn in the trajectory in the field space, which gives rise to this deviation from slow roll. So, varying this action, we can arrive at these coupled equation of motion, and when we solve these, we can obtain the solution of phi and chi, and we can construct the coupling functions in the similar manner. So these are the two models of our interest, which can generate features in the scalar power spectrum, similar to that we have seen in the single field model case. So as I have mentioned in the single field case, what was happening was, when one field was slowly rolling down, and once it faces the point of inflection, it was becoming constant. And which is why our coupling function, which was constructed using the slow roll solution, it was also becoming constant. However, in this case, since there are two fields, when one field is becoming constant, the other field is starting to roll down and is the dominating field in governing inflation after the point of inflection is reached. So these two fields, one after another, drive the dynamics of inflation, and the evolution of the fields never become constant. So if we use such a dynamics to construct the coupling function, so this is how we have constructed the coupling function, one that uses the field phi and other that uses the solution of the field chi, and we have patched them up. These are the four figures that shows that although there is a deviation from slow roll happening at some e folds, however, that behavior is just for a brief period because the second field is taking over, and my coupling function, which was constant for single field, here it has regained its exponential behavior. Just to give a brief comparison with the single field, these two field models also generate the similar scalar power spectrum. This is for the model which generates features over small scales. You can see that there is a separation of power. And this is which generates features over small scales. There is amplification of power in this model. So these are comparable to the features we saw in the single field model case. So these two field models that we have worked with, they also generate similar features in the scalar power spectrum. And when we use the solution of both the fields to construct the coupling function, we can recover the original behavior of the coupling function that we saw in the slow roll model case. So using this coupling function, we obtain power spectra of magnetic and electric field, which are within the required strength and shape that we had expected from the de-sitter case or the slow roll case. And as you can see, there are small features which are not completely avoidable because there are features, there are deviation from slow roll from inflation. However, we can simply integrate over the entire scale in these cases because the features are not in very large in deviating very large from the scale invariant behavior. So we can, while integrating them out, these features can be taken care of. So for both the models, we have computed the present day strength and we see that it is of order of 10 power minus 1 nanogauss, which is way below than the observed strength, which is of order of 1.2 nanogauss. So after generating magnetic fields in the two-field model case, we have tried to study the imprints of the magnetic fields generated in these two-field models on the cosmic microwave background. So for that, we have used the code MagCam, which takes into account the present day strength. There are two quantities which it takes into account. One is the present day strength of the magnetic field, and other is the spectral tilt of the magnetic field. And since here we have a nearly scale invariant spectrum, so we can easily take one of the models into consideration. So we have worked with this second model, which generates features in the scalar power spectrum over small scales, because the first one has a small deviation and the MagCam code is very rigid about using a power law form. So smoothing it, we did not want to tamper with the code. So we just used this second model and we have computed the contribution to the CLs due to the compensated and passive mode. These are the two modes which are generated using this MagCam code. The compensated, so just to give a brief idea, what are these compensated and passive modes? So the compensated modes are scalar perturbations which are generated after neutrino decoupling and after inflation and after neutrino decoupling, while passive modes are the scalar perturbations which are generated before neutrino decoupling. And these two modes, these scalar modes, are sourced by the magnetic field. So the MagCam code, when you give these amplitude and spectral index, it can generate these two modes and show how they contribute to the CLs. Then there is a third kind of contribution to the CMB, that is by the inflationary magnetic modes, which we have computed by sourcing the scalar perturbation from the magnetic field during inflation itself. So we have used CAM because there was a scalar power spectrum, that is a secondary scalar power spectrum, which is generated by magnetic fields. So since it's a scalar power spectrum during inflation, so we have used CAM, we modified CAM a bit, and we have obtained the contribution to the CLs from the primordial magnetic fields. So this is how the contributions look like. So the red one is the standard spectra that we obtained from the primary scalar power spectrum. Then this blue one is the contribution due to the inflationary magnetic mode. The green one is contribution from the passive mode, and the cyan one is the contribution from the compensated mode. And as expected, the blue one has the higher contribution, which is the inflationary magnetic mode. So as of now, as I have mentioned that there are two ways to address the challenges in the single field models. That is, either you rule out the models itself that they cannot generate power spectra. So we need to look for other models which can show the same behavior of the scalar power spectra. However, they can also generate magnetic fields. The other way was to construct a suitable coupling function instead of constructing the coupling function the way we were constructing. So the first one I have addressed, that we can just simply switch the models. We can use some other models, which is two-field models in our case. So the next one I will address is how we can construct a suitable coupling function. So before going to construction of coupling function, I will just briefly show how the slow roll parameter behaves. As I have shown in the figure that there is an exponential drop. So that arises from this, that when you see the Klein-Gordon equation, since the potential here becomes flat, so this term vanishes and we arrive at this equation. This is the reduced equation. And from here, we can see that the first slow roll parameter behaves in this manner. And you can see that this is a e power minus n 6n drop. So that is why there was a sharp drop here. Yeah, so this sharp drop is coming from this particular behavior of the first slow roll parameter. So for our analysis, we have generalized this equation a bit, and we have chosen the coupling function to behave in this manner, that the epsilon 1 behaves as eta power p. Now, we cannot just simply use the slow roll solution anymore. So what we have done is we have used the kinetic energy of the field to construct the coupling function, because if you see, look at this kinetic energy term of the field, it is related to the first slow roll parameter. So what happens during an epoch of ultra slow roll is the field is constant, the Hubble parameter is constant. The only dynamical variable we have which can give a time dependent behavior to the coupling function is the first slow roll parameter. So that was our first goal, that we need a dynamical variable to use in the coupling function which can lead to a scale invariant behavior of the primordial electromagnetic fields in the required strength. So with that goal in mind, we have constructed a coupling function. We cannot directly just put epsilon 1 here. We need to understand the evolution of the field. So which is why we have constructed a coupling function in this manner, which ultimately behaves in this eta power alpha p by 2, where alpha is the power of epsilon 1, which this is our choice of coupling function, which comes from this particular behavior. So for this kind of coupling function, the electromagnetic energy density also is modified. It appears there were no, these coefficient are additional coefficient which appear before the energy density that we have considered earlier. That is when the coupling is just a function of time. And we see that in this case, for this particular choice of coupling function, we can arrive at a scale invariant behavior of PB for this combination to be -4. So this is how the coupling function looks like. This is a theoretical, we have not used numerical evolution of the power spectrum. We have taken the theoretical expression here to plot these. However, in earlier cases, for all the slow roll models and ultra slow roll models and two field models, since the dynamics was extremely non-trivial, so we have computed these power spectra, coupling function, everything using the numerics, and in this case it's just theoretical expressions plotted directly. So yeah, with this, these are the two ways to overcome the challenges in generating primordial magnetic fields in single field models of inflation. So I would briefly summarize my talk, that we saw that models which generates features in the scalar power spectrum due to deviation from slow roll, they also lead to features in the electromagnetic spectra. So but there are certain challenges in single field models which generates features in the scalar power spectrum. Those are, there is a very strong scale dependence on the spectra over small scales. There is a very large separation of power in the electromagnetic spectra over large scales. And to overcome those challenges, we have to extremely fine tune the coupling function for single field models. However, that is also not sufficient to overcome the challenges. So we have two ways to overcome we have proposed two ways to overcome those challenges. One is by changing some other models. So we have worked with the two field models of inflation, which we saw that it gave us the desired shape and amplitude. The next is we have changed the method of constructing the coupling function, where instead of using the solution of the field phi, we have used the velocity of the field, that is the kinetic energy of the field, to construct the coupling function. And in this case also, we can obtain desired strength and shape of the magnetic and electric fields. With this, I would like to conclude. Thank you.
Okay, thank you for the
Feel
nice
free to